Okay, so Pythagorean theorem. Typically, when you ask someone what the Pythagorean theorem is, usually they can regurgitate a squared plus b squared is equal to c squared. That's what really jumps out at people. But yeah, let's get right into it. The theorem actually says that if a triangle is a right triangle, then the square of the length of the hypotenuse, c squared, is equal to the sum of the squares of the legs. So if the legs are A and B, you square each leg and you add them together. And that should equal the hypotenuse squared. And that's the theorem. So this only takes place in a right triangle, meaning a triangle with a 90-degree angle. Some very useful numbers. These are called Pythagorean triples. The most common that you'll see are 3, 4, 5 linked triangles, right? 3 and 4 are the legs, and 5 is the hypotenuse. So 3, 4, 5, and 5, 12, 13. These are the most basic or most common that you'll see in problems. So when you recognize these sides, you know immediately that you're dealing with a right triangle. If for some reason you happen to be taking the SATs coming up, then it would benefit you to commit these two to memory because they are very common. All right, so question becomes, is the converse of the Pythagorean theorem true? So the converse would be if c squared is equal to a squared plus b squared, right? If the square of the hypotenuse is equal to the sum of the square of the legs, then the triangle is a right triangle, right? Because the theorem says that if you have a right triangle, then the calculations are true. But we're saying, well, what if you have the calculations? Does that make it a right triangle? Well, if you happen to have a compass and a straight edge handy, you can construct a triangle with sides 6 centimeters, 8 centimeters, and 10 centimeters. And you would see that, yes, it is true. It is. Discovering or diving deeper into the converse, if we decrease and increase the hypotenuse to either 8 centimeters or 12 centimeters and compare all the angles with the protractor, we would see that the hypotenuse is, if the hypotenuse is shorter, smaller, then it is an acute triangle. If the hypotenuse is longer, then it is an obtuse triangle, right? That there's an angle in the triangle that is greater than 90. So here in this picture, you see that the middle line, this is the line that we just had, that's the right triangle. Now, if you shorten the hypotenuse, it's going to bring the line or bring the side in a little bit. So this angle will be smaller than 90. So all three angles will be acute. When it is exactly at 8, 6, and 10, then you have your right triangle, right? The angle is 90 degrees. And when you extend the hypotenuse out, right? The hypotenuse is always the longest side. When you extend the longest side out, then it's going to force that angle to be wider than 90 degrees. So the things that you want to keep in mind, that the hypotenuse is shorter, it is an acute triangle. If the hypotenuse is longer, then it is an obtuse. We're looking at acute and obtuse triangles in more depth. So in a right triangle, we said that the hypotenuse, the square of the hypotenuse, is equal to the sum of the square of the legs. Okay, well, what we just noticed is that if the square of the hypotenuse is smaller than the sum of the square of the legs, then the triangle is an acute triangle, right? The hypotenuse is short, too short. If the hypotenuse is longer, right? If the hypotenuse is greater than the sum of the square of the legs, then the triangle is an obtuse triangle, right? The hypotenuse is too long. So you want to go ahead and start correlating these two ideas. If the square of the hypotenuse is exactly equal to the sum of the square of the legs, then it is a right triangle, right? The hypotenuse is just right. It's exactly the length that it needs to be to make a right angle. Too short, acute. Too long, obtuse. That's what you want to start making the connection with. All right, so let's see some examples of this put to use. some practical. All right, so when you're solving for x, solving for the missing leg, we have x squared plus 7 squared is equal to 25 squared. Right, sum of the square of the legs is equal to square of the hypotenuse. This is going to be x squared plus 49, 25 squared. So 25 times, I believe, is 625. If we solve for x, subtract 49 from both sides, we're going to get x squared is equal to 576. Take the square root of both sides, you're going to get x is equal to root 576. So let's see if this is a perfect square. In fact, it is 24. So x is equal 24. Okay, number 2. 3 squared plus 9 squared is equal to x squared. A lot of these are going to be very repetitive, right? Finding the missing side of a right triangle. So 9 plus 81 is equal to x squared. 90 is equal to x squared. When you take the square root of both sides, x is equal to 90. Or x is equal to the square root of 90. Our 90 is not a perfect square, so we're going to have to break down 90 into its prime factors, right? Prime numbers, 2, 3, 5, 7, 11, 13, 17, 19 typically. ... right? Like there's infinitely many, but we really only use like the first handful. So this is going to be 3 and 30, 3 and 10, 2 and 5. So 90 is equal to 3 times 3 times 2 times 5. We can pull out a pair, right? A pair can be taken out of the square root as a single factor. So x is equal to 3, right? Because I can pull out a single 3. And then 2 times 5 is left in the radical, which is basically 10. So x is equal to 3 root 10. All right, number 3. 1 squared plus x squared is equal to 2 squared. So 1 plus x squared is equal to 4. If I subtract 1 from both sides, x squared is equal to 3. X is equal to root 3. And that can't be simplified any further, right? It's a prime number. We'll do a couple more, and then we'll get to some slightly harder ones. Okay, number 4. 5 squared plus x squared is equal to 13 squared. So 25 plus x squared is equal to 169. Subtract 25 from both sides of the equation. X squared is equal to 144. That's nice because x is equal to, if you take a square root of both sides, x is going to be equal to 12. 144 is a perfect square. All right, let's see. Let's do one more. So 5 squared plus 6 squared is equal to x squared. Remember, it's the sum of the square of the legs, right? The legs, and it's equal to the square of the hypotenuse, x squared. So we have 25 plus 36 is equal to x squared. It's going to be 71. Is that correct? 5 and 6 is 11. Carry the 1. Oh, no. This is going to be 61. And take a square root of both sides to get x by itself. X is equal to square root of 61. 61, I feel, is prime. There's no two numbers that multiply to make 61. So we just have x is equal to root 61. Okay, let's see. What else we got? Look at number 9. This one's interesting. Okay, so we have a right triangle situation. One leg is 12. The other side is unknown. Or the other leg is unknown, but the hypotenuse is 20. So if we find this side, it's going to be congruent, right? Because that's what the tick marks mean, that they're equal. So if we can figure out what a is, we just multiply a by 2 or add a to a, and we'll figure out what x is. So this is going to be 12 squared plus a squared is equal to 20 squared. So 144 plus a squared is equal to 400, right? 20 times 20 is 400. Minus 144 minus 144, a squared is equal to, going to be 6, 5, 2. So 256. Take square root of both sides. Is 256 a perfect square? I feel like it is. I feel it's going to be like 16, but that is just a guess. Let's see. I do have my Inspire handy. 256 is 16. So a is equal to 16. So if a is 16, x is going to be 2 times a, and that's 32. So x is equal to 32. Okay, area problems. These are always fun. So area is going to be, this is a perfect square. 4 right angles. All 4 sides are congruent, so this is a square. Area is length times width. So let's do 4 root 5 a cubed times 4 root 5 a cubed. When we multiply square roots, we can multiply the coefficients, then multiply the radicand, the part that's inside the square root. So 4 times 4 is 16 times, all right, the square root. Actually, when there's a nice property, when you multiply square roots and the radicands match, then the product or answer is just the radicand. So 5a cubed. Again, because these match, when they multiply, the square root goes away and the part that's left inside is just what you have. So simplifying this, 16 times 5 is going to be 30, carry the 3, 80 a cubed. So the area of this square is 80 a cubed. Kind of interesting. All right, let's look at some different examples. Classify the triangle formed by each set of side lengths. Okay, so this is going back to, all right, so what we're going to do is we're going to analyze the 3 side lengths of the triangle, and then we're going to see if it's a right triangle, an acute triangle, obtuse triangle, or maybe it's not even a triangle at all. Okay, so in a right triangle, right, the hypotenuse is always the longest side. So if I take the 2 legs, square them and take the sum, I'm going to compare that to the square of the big leg. So this is 81, right, 9 squared plus 144, and then 15 squared, 225. So the question is, how does 81 plus 144 compare to 225? So this is going to be 225 exactly. Right, 81 plus 14, or 144 is 225. So they're equal. They're equal. So that means this is a right triangle. Okay, so root 14. So the question is root 14, like, are these all lined up smallest to greatest? That's the question. They look like they're in ascending order. So it's safe to assume that the square root of 14 is the smallest side, is a leg. So if I square root 14 plus 5 squared, compare that to 81, right, 9 squared. This is going to be, when you square root, they cancel, so it's just 14 plus 25, and we compare this to 81. Okay, so here's an interesting situation. So the two sides, legs, are definitely smaller. The sum are smaller than the square of the longest side. However, we could say that this is an acute triangle, right? Just based off of everything that we've talked about. There is one thing that we need to understand is that for this to even be a triangle, right, the two smaller legs must be greater than the longest leg, right? Because if you think about a triangle, the two smaller legs, when you add them up, that length has to be greater than the longest side. If they're not, then it's not a triangle at all. Like if the two legs don't add up, like if you add them up and they're shorter than the longest side, then you would have this situation here where it wouldn't even make a triangle. Like the legs wouldn't even meet at the vertex. So root 14 is actually 3.7 something. And 3.7 plus 5 is just shy of 9. So this is not a triangle. I guess it's worth checking to see if it's even a triangle first. And then if it is, you can proceed. And if it's not, you can just scrap it. So let's look at 14. So 4 and 6, that's 10, which is definitely longer than 7. So this is a triangle. Let's see what kind. So this is going to be 4 squared plus 6 squared. Compare this to 7 squared. So 16 plus 36, 49. This is definitely bigger than 49. So the hypotenuse, right, the 7 squared, is smaller. So the hypotenuse is smaller, so it's too short, right? It's too short because it's smaller. So that means it's going to be acute. Okay, 7, 24, 25. So 7 and 24 definitely are greater than 25. I feel like this is one of the ones that we get to remember. This is kind of ringing a bell, but let's just see what happens. Actually, let's check and see. Let's check. Right, 7, 24, and 25. So, right, this comes in handy. This is a right triangle, right, because it's a Pythagorean triple. 10, 15, 16. I don't believe that was one. Nope. Okay, so 10 and 15 are definitely longer than 16. So 10 squared plus 15 squared, we'll compare that to 16 squared. So 100 plus 225, 256. So it's definitely greater than 256. Again, the longest side of the hypotenuse is smaller, so it's too short. So that means it's going to be acute. 5, 12, 13, Pythagorean triple, right triangle. How did I know that? Because we just looked at the list. That's a right triangle. 5, 12, and 13. 5, 12, and 16. Okay, this is definitely not a right triangle. Not a right triangle. But let's see. So let's think about it real quick. If 5, 12, so 5, 12, 13. If this makes a right, I don't know if this is actually pictorially correct, but I'm just doing a rough sketch. So if this is a right triangle, and we're doing 5, 12, and 16, so 5, 12. So I feel like did the hypotenuse get longer? I feel like this is going to be an obtuse triangle, but it's really Actually, no, we can say that, right? Because we just said that in the notes section, I guess, we said that if you have a right triangle and you extend out the longest side, then it'll open up that angle, right? And it'll be greater than 90, right? This is greater than 90 degrees, greater than 90. So this is definitely an obtuse triangle, using some logic there, and the notes rather. Let's do one more. Since these have square roots in them, this is a good practice. So root 5, 2.2-ish, and 3 root 6, 7.3-ish. Okay, so these two are definitely bigger than the longest side. So this is definitely a triangle. So let's see what happens. 7 squared plus root 5 squared, and then 3 root 6 all squared. So 49 plus 25. Compare this to 9 times 6, which is, right, because we're applying the square. So 3 squared, and then the square root's going to go away. So 54, 49 plus 25. That's actually 54. They're equal. It's exactly equal. Oh my goodness. All right, so this is going to be a right triangle. Right triangle. Let's do a couple word problems, and then I think this will be good for Pythagorean theorem. I'll probably just do the left side. And if you want, you can pause the video, practice on the right side. Or practice on the problems that I didn't do. Actually, we'll just do 22 and 24. Let's do 22 and see what happens. All right, so the perimeter of a square is 36. So a square is drawn here, and the perimeter, so if we call this A, the perimeter is going to be 36. So that means A plus A plus A plus A. So we're adding up all four sides. So this is going to be 4A, and 4A is going to equal 36. What is the length of the diagonal? The diagonal goes from corner to corner. Call that C. So we're going to get, what are we going to get? Let's figure out what A is. So divide both sides by 4 to solve for A. And A is equal to 9. Because 36 divided by 4 is 9. Okay, so if this is 9 and this is 9, the diagonal is going to be equal to the sum of the square of the legs. So 9 squared plus 9 squared is equal to C squared. This is going to be 81 plus 81, which is 162. And that's equal to C squared. So C, I take the square root to isolate C. C is going to be equal to root 162. That's an exact number. So we'll leave it exact. 162. It's going to be longer than 9 for sure. So if you want to know, 12.7-ish. I think that's good. That should be good. If this wasn't a Pythagorean theorem lesson and we had a problem like number 24, the question is, would you be able to understand that you would have to apply the Pythagorean theorem in this situation? That's truly the question. So a flagpole has cracked 9 feet above the ground and fallen as if hinged. The top of the flagpole hit the ground 12 feet from the base. Write a simplified expression to represent the original height of the flagpole. So the unknown side Write a simplified expression to represent the original height of the pole. Okay, well, the original height of the pole is going to be x plus 9. Right, 9 feet off the ground, and then however long the pole is. But let's figure out the exact length of the pole, shall we? This is going to be 9 squared plus 12 squared is equal to x squared. 81 plus 144 is equal to x squared. This is going to be 125 is equal to x squared. Square root. 125 is not a perfect square, but it is 5 times 25, 5 times 5, so 5 root 5. So x is going to equal 5 root 5. Which, if you're curious, is a little bit more than 11, 11.1. So approximately, right? It's not exact. So it was about a 20-foot pole, a 20-foot pole. All right, so hopefully you found this video useful. If you haven't already, go ahead and subscribe, like, comment, let me know what you think, and be sure to hit the notifications bell so you never miss a video. I'll see you in the next video.